So in a previous lesson, I had alluded to the idea that in Pascal's triangle, that the sum of a row in Pascal's triangle is a power of 2. I'm going to answer that question now using the binomial theorem. So just to tell you what we're going to prove, so this is a very common closed form, regardless of its meaning within Pascal's triangle. We're going to prove this. First, we're going to use the binomial theorem to do this, and then I'm going to give you a different way of looking at the same thing from a combinatorial point of view. So here's a theorem. For any non-negative n, specifically, I should say non-negative integer n, the sum from k is equal to 0 to n of n choose k is equal to 2 to the power of n. Now, you might be staring at this like, okay, so how does this answer the question? Well, just as a quick reminder, let me remind you of what Pascal's triangle looks like. So I got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. So my claim previously, and remember, that comes directly out of this theorem, what we wanted to know about this, because in a previous lesson I told you that if you add up the rows, so if I sum up these numbers across the rows, if I add them up, each one's a power of 2. So I have 1, 2, 4, 8, 16, and so on. Why is that? Because each one of these rows is this sum. So let's prove it now. So this is going to be an algebraic proof. But remember, under the hood, we had a combinatorial argument for this, but you can go about it in other ways as well. So applying the binomial theorem, so what should I apply the binomial theorem with? So remember, the binomial theorem has this form, right? A plus b to the power of n is equal to something that looks kind of like that, but it has like an a times a b where each one has exponents in it. In a previous exercise, we noticed that if we just put 1, as a, for example, you end up with just something that always results in 1. So why don't we try something? I'll make sure that this is 2 to the power of n. So maybe make a1, b1, and we'll see what happens. With a is equal to 1 and b is equal to 1. So we end up with this. So now, 2 to the power of n. So I'm starting on the right-hand side. This is equal to 1 plus 1 to the power of n. But this is equal to the sum from k is equal to 0 to n of n choose k of 1 to the power of n minus k times 1 to the power of k, right? That's what the binomial theorem says. Then this is just 1 always. That's 1 always, right? So this is just times 1 times 1. But then this is all just this. The sum from k is equal to 0 to n of n choose k. And that's it. That's the proof. Very short, very simple. So that's how you could prove this claim that the rows of Pascal's triangle are in fact powers of 2. Comes out of this theorem.